Well, thank you so much for having me for giving this talk. It's a very nice opportunity to present today. So yeah, I'm Emanuele Dalsasso, and I am a research scientist with Inria in France, in Grenoble, since December of last year. So today I am planning to present you the work that I did between my PhD thesis and also my postdoc. And so it's a work that I've done with many other people. So I would like to start by acknowledging them. First of all, my PhD supervisors, Loïc Denis and Florence Dupin, with whom I have done most of the works that I would be presenting today, and also Clément Rambourg, Nicolas Trouvé, and Nicolas Thome, who also have worked with me on some of the projects that I will present in the second part. I structured the presentation of today mainly in so it's three parts, but the second one is very quick, is very broad. So the two main parts will be related. The first one on self-supervised learning for despeckling, and I will present MERLIN, which is a self-supervised despeckling method. And then the second most important part will be more on representation learning using self-supervised methods for specifically for SAR images. So let's dive in, and let's start with the first part on self-supervised learning for SAR data. And well, so as you are all well aware of, we have all this like wide variety of sensors that are orbiting around our planet, and so the focus of today is synthetic aperture radar, which it's an active sensor, which means that it sends a wavelength. It sends an electromagnetic wave. What's nice about radar, especially, is that well, given that it's an active sensor, it's independent on sunlight, and also the specific frequency at which the wavelength is sent makes the radar independent basically on weather conditions. So it means that the electromagnetic wave can penetrate through clouds and rain, let's say. So it's an all-weather and all-time sensor. So that's very nice because it can complement especially optical images when there is a very dense cloud cover, for instance. But the problem of radar is that they are impaired by some very strong signal fluctuations that we call the speckle. So let's see, here we can compare an optical image with a radar image over the same area, and we can see that an area that is physically homogeneous presents in the radar signal strong fluctuations. So here we can compare the two histograms, and we see that indeed in the optical image, the histogram shows that values are quite homogeneous, while the same area, again physically homogeneous, presents a long tail distribution in the radar signal because of some fluctuations that are intrinsic to all coherent imaging systems. So a coherent imaging system is a system that acquires the phase on top of the amplitude of the backscattered signal. And the reason why we have those fluctuations is that within a given resolution cell, we have many elementary scatterers.
Sorry, Emanuele.
And each of them...
Sorry, Emanuele, to interrupt you, but in the chat from the Phi-Lab,
yeah,
they are asking us if we can interrupt or pause the presentation because they still have some issue. I'm super sorry for the people online. Be patient. They will solve it.
It's okay. It's okay.
Okay.
Problem solved.
Okay. Problem solved. Okay, great.
Yes.
You can go ahead.
Can come back.
Perfect.
Okay. Yeah, so I was saying within a given resolution cell, so within a given pixel, basically, we have independent, we have several elementary scatterers, and each of those scatterers, which correspond to all these gray arrows, conveys a signal. And so the contribution of each of these elementary scatterers can interfere in a constructive or in a destructive way. And this gives rise to a signal that presents strong fluctuations depending on the way those elementary scatterers interact between themselves, which creates those like sort of speckles indeed that we see in the image. So an area that is physically homogeneous can react in many different ways depending on the geometric arrangement of the elementary scatterers within the resolution cell. And so from a statistical point of view, we can model the real part and the imaginary part as Gaussian, as variables who follow a Gaussian distribution. And the complex SAR signal indeed follows a complex circular Gaussian distribution. And then the intensity, which is what we are seeing on our screen, it follows a gamma distribution, which has an heavy tail. And that's different from an optical image, which doesn't present this type of statistics. Moreover, the other difference between, well, the natural images world, so the computer vision world, and radar images is that in natural images, typically the noise is Gaussian distributed and it's additive, while in the radar signal, the noise is multiplicative. So it means that the amplitude of the fluctuations depend on the underlying signal. So the more the underlying signal is high, the stronger will be the fluctuations that you observe in the radar. So this calls for specific tools for reducing the speckle from SAR images. So the speckle is modeled as a random variable and is treated as a multiplicative noise. So we can define an intensity image, which is what is measured by the radar, as the product between the underlying scene, which is the reflectivity, and the speckle. However, in real images, due to the specific processing that is applied by data providers, the pixels of the radar signal and the pixels in the speckle component, they are spatially correlated. And this assumption is often not taken into account by denoising methods, which assume that the noise is independent and identically distributed spatially. And what happens if we don't take into account the spatial correlation? Well, it happens that if we process an image with the assumption, with the underlying hypothesis that pixels are IID, the denoising method, whether it is non-deep learning based or even deep learning based, it will create many artifacts in the scene. And what you observe is that if we, for instance, subsample the image by a factor of 2, so in this way we destroy the spatial correlation, we have a very smooth result. But the problem is that by subsampling the image, we reduce the resolution by a factor of 2. So it means that we discard half of the information contained in an image, which is not desirable. So the question is, how can we develop methods that can depart from the theoretical model and can integrate the underlying knowledge and the specific statistics that are inherent to real images? So SAR despeckling is a problem that has been studied since the 70s and the 80s. And it has been tackled through several by several methods. So the first more basic methods consist in averaging pixels within a window of a fixed size, and then those methods have been refined to more more sophisticated patch-based methods where similar patches within an image are averaged together to reduce the fluctuations linked to the speckle. It has also been studied through the eye of Bayesian methods, and then finally, most recently, it has also been tackled with deep neural networks. So let's see how we can tackle SAR despeckling with deep neural networks. So in a classical denoising framework, we have an image that doesn't present any noise. So we have a ground truth image, which is noise-free. And in a typical computer vision pipeline, we add additive white Gaussian noise to this image so that we can generate pair of noise-corrupted and noise-free acquisitions. And then we feed the noise-corrupted observation Y to a neural network. And then we ask the neural network to produce an image that should be as close as possible to the ground truth according to some distance. The problem with SAR despeckling is that, so by nature, the images are corrupted by speckle, so we don't have access to any ground truth image. So that poses the question of which training data set to use and which training strategy to set up. And also, the speckle doesn't follow an additive white Gaussian distribution. So how can we inject prior knowledge about the speckle in order to develop methods that are tailored for the specific statistics of the speckle? So which loss function should we use, given that the distribution of SAR images is different from that of natural images? So in this presentation, I will provide one answer to all of these questions, which is based on the advancements in the computer vision field in self-supervised denoising. So let's see what a self-supervised denoising framework looks like. So in a classical supervised framework, again, we ask the model to minimize the distance between the output of the model and the ground truth. So if we consider the case of the L2 loss function, we have the minimum of this loss function will be exactly at the position of the ground truth. It has been demonstrated in the noise-to-noise paper that if we replace in the L2 loss function the ground truth by another independent noise realization, and under the hypothesis that the noise is centered, so it means that the mean of the noise is equal to 0, then by optimizing this loss function through the iterations, we will end up having finding that the minimum of this loss function will be at the same position as that of the ground truth. So asymptotically, if we can have an infinite number of iterations, we would find that the optimization of this loss function will be at the same position as that of the ground truth. So we will end up denoising the image. And from a more intuitive perspective, so if we consider a given scene and then we corrupt the scene with two independent noise realization, we end up having two images whose common information is the underlying scene. And then at each pixel, the noise would be independent between Y1 and Y2. So if we task the network to estimate Y2 given Y1, this task is impossible to solve because of the independence of the two noise realizations. So the model cannot do better than predict the common information between the two scenes, and the common information between the two scenes is the ground truth. Well, that was demonstrated for the case of the L2 loss function, but actually this property is much more general. And if we know the distribution of the noise at each pixel, we can actually replace the L2 loss function with the log likelihood of the noise model, which in our case has this specific formulation. And so the log likelihood is directly derived from the Goodman's model of speckle. So it's a way to guide the learning of the model by introducing prior physical knowledge about the model of the noise. So let's see how we can leverage this self-supervised framework in order to set up a self-supervised despeckling method that is tailored to SAR images. The literature in this domain, so again, the basic intuition of self-supervised denoising is that we need to identify two independent like components of the image. And so these independent subcomponents can be identified, has been identified in the literature in three different ways, either by relying on time series, so by exploiting the temporal diversity. But the problem of this method that we worked on, and it's the SAR2SAR algorithm, is that it requires to have access to time series of images, which is actually not always the case. And also we have changes between the images. So the underlying scene is not the same. So this needs to be taken into account, and it's a bit cumbersome in the training to be able to do that. Another way to identify diversity in the samples is by masking. So we can extract some pixels from the image and hide them from the input, and then ask the model to reproduce those masked values. And that's the speckle to void algorithm that was produced by that was proposed by Molini and colleagues. But the problem of this approach is that it needs the speckle to be uncorrelated, which is not the case for real images. So the image has to undergo an uncorrelation pre-processing step, which is not easy to perform, and also it requires to know the specific metadata of the image that is delivered, and we don't always have access to this metadata. So today what I would present is a very easy way actually to cope with this problem of obtaining two components who are independent, and it exploits the real and imaginary part diversity. So let's see how. So if we have a look at a generative model of SAR images, so we have a reflectivity, which is our clean underlying scene, and the reflectivity is multiplied by the complex speckle. So the complex speckle is composed of a real part and an imaginary part. The real and imaginary part, they are spatially uncorrelated, and they both follow a Gaussian distribution, and they are independent between each other. Then the SAR image undergoes the SAR system, which introduces some spectral apodization and also some zero padding in order to reduce the side lobes of strong scatterers, and also to generate pixels of the desired size. And this generates our single lux complex image, which is delivered by image providers, where in the real and imaginary part, and also in the SAR image, the pixels are spatially correlated, but the real and imaginary part, they remain independent between each other. So this creates the perfect framework for setting up a self-supervised despeckling method, because we have access from a single intensity image. We can decompose the intensity image into the squared real part and the squared imaginary part. They are independent, and they both they are both acquired at the same time. So there are no changes between the real and imaginary part. And we can learn the model directly on real images, which means that we can integrate the knowledge about the spatial correlation. So the model can be deployed directly on real images. So it seems pretty trivial, actually, when we look at it like that. But historically, when we have a single image, we tend to discard the phase information because it's uniformly distributed between -pi and pi. So that doesn't bring any additional information. So people only look at the intensity. And so it was a bit shocking, actually, when we discovered that by exploiting the phase information, we can divide the intensity image into two independent subcomponents. And so that's why we called the method MERLIN, because it was a bit magical. And the model works in the following way. So it's a self-supervised training strategy. So in a way, it's independent on the despeckling network that you want to use. Its setup is very simple because you only need to take a single loop complex image, isolate the real part and the imaginary part, and then you can feed one of the two into the model and use the other one to supervise the training. And then the loss function is again derived from the statistics of the speckle, and it's the negative log likelihood of the estimated reflectivity by the model and the part that we are using to supervise the training. And then at inference time, given that the model is trained to produce an estimated reflectivity from either the real part only or the imaginary part only, then at inference time, we would process separately the real part and the imaginary part. We would get two intermediate estimation of the reflectivity that we can average to get the final estimation of the speckle-free scene. So due to the fact that it's very simple to set up such a training strategy, we have trained one model specific for each sensor, and we have tested it on different sensors. So here we can see some results on TerraSAR-X in strip map mode, and where we can see the intensity image that was decomposed into the squared real part and the squared imaginary part. They are both processed independently by the same model, and then the two intermediate results are averaged to produce the final estimate. And we can see that with MERLIN, we can directly process real images without any pre-processing. It accounts for the specific, it implicitly learns the spatial correlation that is inherent to each sensor. So it produces a result which is very nice. The homogeneous areas are smoothed as we want to, and then we preserve very well the textures in highly textured areas. So it allows to very well preserve the fine details of the image without introducing artifacts. We also trained a model on TerraSAR-X images in spotlight mode. So it's a very high resolution image modality. And so this experiment shows that the model works also at a very high resolution. So here we are speaking about a centimetric resolution, like I think that it's like between 30 and 50 centimeters, the resolution. And then we also went even further, and we applied the model on an airborne image that is operated by ONERA, which is the French aerospace lab. And it's at 35 centimeters, the resolution. And here we can compare the optical image with the single look radar image, and we can observe the quality of the denoised result. If we compare the result of MERLIN with other state-of-the-art methods, such as speckle-to-void as a deep learning method, and then SAR BM3D. What we can observe is that, especially by looking at the residual noise, we expect the residual noise to be homogeneous, to be stationary, actually. And the more we see structures in the residual noise, the more it means that we have suppressed some structures in the image, or that we have introduced some biases. And here we can see, for instance, that the residual noise for the two other baselines, it presents much more structures. So this, again, highlights the high quality of the reconstruction of MERLIN. And even if we, again, zoom in, we can see that the two baselines, they struggle much more to reconstruct the fine details, and they tend to oversmooth some areas. And again, even when we look at a spotlight image, we can see that the residual noise is much more textured, and the models seem to fail when it comes to very bright areas or very dark areas here. So they introduce biases in the denoised estimate, which is not the case for MERLIN, that produces a speckle-free image that doesn't produce any, that doesn't show any clear bias in its estimation. So it seems to be highly accurate, to preserve the fine details, to preserve very bright scatterers, and it doesn't seem to introduce any artifacts in the speckle-free image. So I didn't speak about numbers yet, because we train MERLIN directly on real images, and on real images, by definition, we don't have any ground truth. So we cannot easily evaluate quantitatively the quality of the results. So we did an experiment by taking some synthetic images on which we simulated speckle. I just would like to stress out the fact that the speckle that was simulated is IID. So it means that it doesn't show the spatial correlation that is inherent to real images. So on this type of images, MERLIN is competitive with the other deep learning approaches. The results are very close to the considered baselines, which is very nice. But the main advantage of MERLIN is that it can be easily trained on real images, and that it can directly ingest real images at inference time. So it's on real images that MERLIN really shines. And that's something that we struggle to measure quantitatively, but we can appreciate when it comes to setting up the training strategy, and when it comes to applying MERLIN directly on real images without having to do any pre-processing on them. So just to summarize on this part, we have seen here that one very effective and easy way to set up a self-supervised despeckling strategy is by exploiting the real and imaginary part diversity of a single look complex image, and that we can use an unsupervised loss that is directly derived from the statistics of the speckle. So it's a way to ingest some prior physical information about the speckle statistics, and that the training strategy that we set up is robust to the spatial correlations of the speckle that the model has implicitly learned directly from the input data. So I think that we can maybe stop on this first part and already take some questions, because it was already quite dense. So if you have some question now, I propose you that we maybe take some time to do a first Q&A session, and then have a second one for the second part of the presentation. Yeah, so I see that there's a question on the chat. I hope that I have answered during the presentation, but Hamish, if it's still not clear, please type a message in the chat and I will go more into the details. Otherwise, I see that there's Vahid who is raising their hand. Please.
Hello.
Hello.
Thanks a lot for your excellent presentation, Emanuele. My question is that you showed the results on single complex images with just one channel. What about the multi-channel dataset? Because sometimes maybe speckle might be statistically different for different channels. So if you train your model based on this VV channel, what happens if you just use the model trained and use it for another channel, for example?
So the model would generalize to other channels because the statistics of the speckle are the same. It's just that by despeckling each channel independently, you would not be as good as if you were to despeckle all channels at once, because you would have much more information by jointly processing all the polarimetric channels. That's something that actually we did. And I will not have time to talk about it, but I put the reference here in my presentation. So I will briefly show that it is possible to extend the self-supervised methods to both interferometric and polarimetric SAR images. Yeah, I will not have time to cover that in this presentation, but you would see the reference, and then you can also contact me so that we can chat about it.
Thank you very much, Emanuele.
Thank you. Okay, if there's no more pressing question, I will move to the second part, and then we will have another Q&A session at the very end as well. Yeah, I presented a specific contribution, but actually this self-supervised training strategy has actually paved the way for many developments in the processing of SAR images. So first of all, the algorithms that we developed, they are published as a Python library that is called deep despeckling. So feel free to play with it and to apply our models on the data. Just be careful that each model is specific to a given sensor, so it has to be applied on that specific sensor. Then we have also used despeckling as a pre-processing step that shows that it improves the performance of downstream tasks. And we have tested it on reverse segmentation and also on CI's classification. And now the paper has been published. I should have updated this slide, so you would find the publication on TGRS. We have also extended our self-supervised methods on on the processing of multitemporal stacks of SAR images. And then we have also shown how the introduction of an optical image can benefit the restoration quality. Finally, we have also extended, actually, we didn't extend MERLIN, but we extended SAR to SAR for the despeckling of polarimetric covariance matrices. So we, in this method that we proposed, that is called PolSAR to PolSAR, we dealt with complex covariance matrices. They are fully covariance matrices, and we demonstrated how those self-supervised learning techniques can also be extended to fully polarimetric covariance matrices. And then the last approach that was developed, it's a way to rely on single-channel despeckling methods to process multi-channel single-lux complex images, whether it is well, any type of covariance matrices actually. So it can be interferometric images, polarimetric images, or INSAR images. I don't have time to go more into the details in this this presentation, but you have the references here. And then, I mean, for any question, don't hesitate to drop a message. But so in the second part of this presentation, I wanted to cover a bit the topic of representation learning for SAR images. Well, first of all, in remote sensing, in Earth observation in general, we have access to a huge amount of data, and only a small portion of it is annotated. So this is a great, I mean, it calls for self-supervised learning techniques that can learn some features on the amount of unlabeled data, and then the features that are learned are transferable to downstream tasks with a reduced annotation cost. So there exist two main families of self-supervised learning strategies that are contrastive methods or generative methods, such as the masked image modeling, which is maybe the most the one that is mostly employed in modern geospatial foundation models. The main problem actually of contrastive strategies in particular for SAR images is that they typically rely on some augmentations, among which I put also masking. And those augmentations are not directly applicable to SAR images, and we will see later why. And that's actually why like those contrastive methods have been widely applied to optical images, but it's not easy to extend them to SAR images. And then also most recently, I mean, we have seen the development of a huge amount of foundation models for Earth observation data. I think that there exist more than 70 foundation models for remote sensing, and they mostly focus on either multispectral images, or when they are multimodal, they only focus on GRD SAR data. So they don't take into account SAR images in the SAR geometry. And they don't account for interferometry, polarimetry, and all the other capabilities that we have with SAR sensors. So let's see how we can set up a self-supervised learning strategy for SAR data. What I will present you now, it's not a foundation model. It's an attempt that we did in 2022 to learn a representation of SAR data in an unsupervised way by taking into account the specificities of the SAR signal. So the question that we were asking ourselves was how we can learn a transferable representation of SAR data, because directly applying the typical augmentations and the typical strategies that are used in computer vision and in optical remote sensing is not applicable directly on SAR images, because the SAR signal is complex valued, it is corrupted by the speckle phenomenon, and also the SAR has a specific side-looking geometry, so you cannot directly like turn the images or mirror them, because you would introduce some unwanted invariances in the model. So the features that you would learn, they wouldn't be as useful on your downstream tasks. So the question is, we have a SAR image. How can we define augmentations of SAR images so that we can set up a self-supervised learning strategy? And actually, our claim was that you don't need to augment SAR images because they are inherently augmented. Before I have said that, I mean, we can actually consider that the real SAR image is the underlying scene, so the reflectivity, and that is augmented by the presence of speckle that generates the intensity image. So we can see the real and imaginary part as two augmented views of the same scene. And in this way, we can rely on MERLIN as and thus we can rely on self-supervised despeckling as a pretext task to learn a rich representation of the SAR data without having to augment SAR data and without introducing some unwanted invariances in the data. So we directly exploit the nature of SAR data in this framework. So when we want to learn a meaningful representation of the data, one would like to train the model on a diverse set of vision tasks. So we have low-level tasks such as image reconstruction. In our case, there would be SAR despeckling. Then we want to train the model on semantic tasks. And in our case, we choose building segmentation. And then you also want the model to learn some geometric features. And in our case, we worked on height estimation. So the first model that we came up with is called MERLIN seg, that at the same time performs the speckling on a so it takes both the real and imaginary part into a common encoder, and then we have two specific heads, one for the speckling and then one for segmentation. And then we train a model to simultaneously reduce speckle and then segment buildings on the image. And the intuition behind that is that even if we have a set of images and only a portion of the data is unlabeled, the model would always train the common backbone on self-supervised despeckling because it doesn't require any annotations. And then for the few samples for which we have annotations, the model would co-learn segmentation on the subset of the data by still benefiting from the features extracted from the speckling. And so here we see that by training the model across different labels percentage, so here we see a model for which 100% of the dataset is annotated, and we compare the results to the case where only 1% of the labels are annotated. And we see that for MERLIN seg, the results are very stable, and that for the other baselines that we consider, they, well, both have a high false positive and also false negative rate because they miss some buildings and they also hallucinate some others. And we see that the results is not stable as we reduce the number of labels. So it really shows that the speckling is an effective way, is a very efficient pretext task that can extract meaningful features for downstream applications. And we have also shown numerically that MERLIN seg is clearly the best when we have a few labeled samples and a limited amount of labeled images. And then we finally extended it to a multitask learning framework, where again we have a common encoder that is always trained on self-supervised despeckling. And then we have two heads that are specific for semantic segmentation and for regression, so for height estimation. And so through this multitask strategy that we have tested on TerraSAR X images, again, we can see that so if we start from a data set where all the samples are annotated, well, our MERLIN multitask performs better than the same model that we used in MERLIN that we consider as a baseline, but it is only trained on segmentation. And then especially the gap becomes bigger and bigger as we decrease the amount of label data that are available. And here we can see that the gap between MERLIN multitask and a baseline unit is very high. So it shows that, again, the speckling is very effective to compensate for the lack of annotations. And the same thing can be shown on height estimation, where we have the error is reduced already when we have 100% of samples that are labeled. And then when we have only 1% of the data set that is annotated, there is a very big gap between the image-to-height baseline and MERLIN multitask. We can also see that qualitatively, because we see that when all the data set is annotated, we have good results for height for building segmentation, but then the unit produces a very not accurate result actually when we don't have labels, whereas MERLIN multitask remains stable across different percentages of annotated samples. And the same can be seen also for height estimation, where we have a good result even when only 1% of the labels are annotated, and we see that the considered baseline completely fails when only few samples are provided to train the model. And then finally, we did an ablation that shows that combining segmentation, regression, and the speckling leads on average to the best result for height estimation and semantic segmentation. So combining these two tasks of segmentation and regression with the speckling really helps, especially when only a limited amount of annotated data is available. So just to conclude on this second part, we have demonstrated that MERLIN multitask can learn semantically meaningful and geometrically meaningful features. It's what we propose is a learning strategy. So this is independent on the specific architecture and on the specific encoder that you use. And then given its flexibility, it can potentially incorporate additional input information that can be in the form of additional polarimetric channels or additional temporal images or optical images, as we did for the speckling before. So let me just conclude this presentation with some perspectives. So in remote sensing and in Earth observation, we have a wide variety of sensors, and they all differ in terms of which specific part of the electromagnetic spectrum they cover. We can have different bands. We have sensors that are only acquiring information in the RGB bands. We have multispectral sensors. We have radars. So they differ in terms of spectral resolution. They also differ in terms of spatial resolution. And finally, they also differ in terms of temporal resolution. So we need a foundation model that is capable, of learning this unified representation across all this variety and this diversity of remote sensing sensors. And we have seen a lot of models being proposed in the past 3-4 years. And when it comes to SAR images, all these so-called foundation models and multimodal models, they only focus on ground range detected SAR images. So they are not images which are in the SAR geometry. They are reprojected into the ground geometry. So we lose the phase information, which means that we cannot exploit the correlation between the polarimetric channels, which is encoded in the phase. We cannot exploit the interferometric capabilities. And so it's a bit deceiving because SAR is just treated as if it was an extra band. And again, SAR, in my opinion, is much more than simply GRD data. And there are only few attempts to develop a foundation model for SAR images so far. Well, we have listened a few weeks ago to the presentation of Jonathan Prexel, who presented SAR-Former, which is a very, very interesting piece of work, which allows to extract geometric features from SAR images. And I think that it's a very nice piece of work that could pave the way for more developments to tackle the whole diversity and the whole multimodality that we can see in SAR images. That is about processing the interferometric channels, the polarimetric covariance matrices, and then Pauling SAR and tomographic SAR stacks. So thank you very much for listening to this talk. I would be very happy to take questions, even offline, if you have any curiosity that comes up by email. And then I would like to do some job advertisement, because I am partner of an Horizon Neuro project that is coordinated by the DLR, so the German Aerospace Center. And the project will start in June, and I am looking for a postdoc to join me in Grenoble to work on onboard processing of SAR images. So if you're interested and you want to know more about the project, let me know. Don't hesitate to contact me. I put my website here. You will find my email address. So if you're interested, please don't be shy. I would be happy to discuss with you about this project that is about to start. Thank you so much.